Hey boys and girls, welcome to another video. Today we're going to be solving exponential and logarithmic equations. This goes with section 8.6 in your textbook. And let's see, objectives for today. Well, we should be able to solve at least two exponential equations. We're going to do three exponential equations, but hopefully at least two of them you can latch onto. And we're going to look at two logarithmic equations as well. For today, for this first lesson, we're going to stick with some of the basic exponential log equations. Not that they're real easy, but we're not going to amp them up too much. We'll see that in later lessons. So let's just jump right in. So we're going to solve an exponential equation, and this one's a little bit unusual. We're starting off with an unusual one right away, and as the title suggests here, we're going to solve by equating the exponents. So when you look at this equation, notice how there's two x's. There's an x in the exponent for 4, and there's an x in the exponent for 8. So I can't just unwrap here. I'm not allowed to do that. I don't have a way of doing that here. But what we should notice is that 4 and 8, those can be written using the same base. Now I can't use base 4. They both need to change, right? 4 is really 2 squared to the 3x. And 8 is really 2 cubed to the x plus 1. So what I'm doing here is I'm writing them with the same base, and then I'm going to, as the title says, I'm going to equate the exponents. Okay, so let me move this down a little bit. Well, I'm going to use a power rule here. So this is going to be 2 to the 6x, right, because I multiply those exponents. And this is going to equal 2 to the 3x plus 3. Make sure you distribute that 3 properly to the x and to the 1. And now I have 2 to the 6x equals 2 to the 3x plus 3. And what's nice about this is because the bases are the same, there's actually an operation going on here. I'm going to skip over that idea though. But these exponents should be the same, right? So I can really just get rid of the 2's. And I can say that 6x equals 3x plus 3. And now we're down to what is, in this case, just a nice little algebra 1 problem here. I can subtract 3x from both sides. I don't need to tell you from here, right? Okay, so I'm going to clean this up a little bit. I get x equals 1. And with these, I'm certainly going to go back and check this and make sure that this works out. So I'm going to put in 1 for x on both sides. And I get 4 cubed, which is 64. And I get 8 squared, which is also 64. So these are the same, so this is my check, and I know that my answer is right. And it actually does work in the original problem. So again, I know that x plus 1 is an answer I'm going to keep. It's not extraneous. Later on today, actually we're going to see this more in the next lesson. We're going to get some extraneous solutions. So checking these is really going to be important. More so with the logarithmic functions actually than the exponentials. Okay, let's move on to another one here. This tends to be a little more of the type of exponential function that we're going to see. We have 2 times 5 to the x equals 42. So notice how there's just one x. And just like any other equation that we've seen so far this year, when you have just one x, we just want to unwrap. So think about what happens when you put in something for x. Well, you raise 5 to the x, right? You do 5. First thing you do is you do 5 to the x. And then you're going to multiply by 2, right? Okay, so we're going to unwrap those in reverse order, right? I'm going to divide by 2 first. Okay, so I'm going to divide by 2. And I'm going to get 5 to the x equals 21. Okay, and I need to leave a little space for myself because I know what's coming up here. Okay, so look at what I want to do. I want to unwrap this 5 to the x, right? I'm underlining it over there. I have 5 to the x right there. I want to unwrap exponentiation. Well, we talked about how exponents and logarithms are inverses of each other. So if I'm going to unwrap exponentiation, I'm going to take the logarithm of both sides. So I'm going to write log on both sides. That's why I left the space in there before the 21, because I knew I was going to write log in there. Okay, so a big hint for you here. What's the base? If you cover up where it says log, right? What's the base in that expression? Well, it's 5, isn't it? Okay, so when I take the log of both sides, I'm going to choose wisely here. I'm going to choose base 5 on both sides. And now look what happens on this left side here. My base in the log and my base in the exponent are the same, right? Or in the exponent expression are the same. So this is going to unwrap nicely, isn't it? This is going to unwrap and just get x on the left side. And on the right side, I'm going to have this expression of log of 21 base 5. That's something I can just put in my calculator and get an answer for. I can leave it like that if I want to. I'm actually going to put that in and get an approximation for us here as well. Okay, when I do that, I get an answer of about 1.892. And if you're not sure, again, this is our nice exact answer there, right? Log of 21 base 5. That's actually fine if you leave it just like that. A decimal approximation is going to be 1.892. If you forget how to use your calculator to use the change of base, or to put that log of 21 base 5 in there, go watch the video on 8.4, I believe. Might be 8.5 that has the change of base property in there. Okay, so that's our basic idea. We're just unwrapping here, and we have this new operation of taking the log of both sides. And again, choose wisely. We had base 5 in our expression, choose log base 5. Okay. Let's look at another one here. This one's amped up a little bit, really only in the fact that I have more operations to do, not that there's anything new for us to get out of this problem. So when I look at this problem, again, you might want to be orderly about this and make a little list for yourself. Like, what happens when you put in x? Well, when I put in x over here, I multiply by 2. Okay, what happens after that? Well, then I subtract 3. Right, that's the second thing that happens. Minus 3. Okay, and what's the third thing that happens? Well, then I do this 10 to the 2x minus 3. 10 to the exponent. Okay, and then you're going to add the 4, right? And then you're going to add 4. So, and again, you can write those out if you don't see it, but if you see that, there's no real need to write out that list. It's just a little helpful thing to see. But I'm certainly going to want to subtract this 4. I'm going to do those reverse operations, right? And start cleaning this up. Okay. And again, the only thing that's amped up about this is that there's more operations to do. Not that there's anything extra fancy going on with this problem here. Okay. So what do we want to do next? Well, we want to undo this 10 to the part, right? Okay. I want to unwrap this part here. Okay. So I'm unwrapping exponentiation. This is the new stuff right here. I want to take the log of both sides. Well, what base do we want to use? What's the base that we have here? Well, it's base 10. So that's actually really nice, isn't it? Base 10 is great because I can just write common log on both sides. I have a button for that in my calculator, and everything's going to work out real nicely here. So again, the whole reason why I'm choosing base 10 is because that log, base 10, and the 10 to the part completely unwrap. And I'm left with 2x minus 3 on the left side equals the log of 17. Okay, and now I'm just going to keep on unwrapping this left side here. I'm going to add the 3, I'm going to divide by the 2, and everything hopefully is going to work out really nicely here. A little note to look out for as I work through this is I can't combine this log 17 and the plus 3. It's really, it's kind of like that in parentheses, where it's really separate, right? So I can't say that's the log of 20. Don't do that. This is just log of 17 plus the log of 3, even with this division. There's really nothing else I can do with this. So I'm just going to get this wonderful looking expression like that. And that's fine. You can leave it like that. If you want decimal approximation, by all means, go ahead and put that in your calculator. But it doesn't really change the fact that I've unwrapped this properly. So hopefully you see this really just as an extension of things that we've done already. Where the new stuff here is we're just using the logarithm as a way to unwrap exponentiation. And we're going to see that continue on the next problem here, where we start with a log function, and then we're going to use exponentiation to help us unwrap. So again, it's a new operation that's going to help us to really just unwrap and get out what we want to solve for here. Okay, so let's solve a log equation. We'll do two of these. This first one definitely is the second one's real nice and easy. The second one's gonna be a breeze. You'll see. And I don't say that lightly. It really is a nice simple one here. This one here, it's not bad. So let's just take a look at it here. Okay. Again, I'm thinking of I have one term with an x. I want to unwrap. Okay. So again, I'm going to make a list of the operations that happen when I put something in for x. Well, the first thing I do is times 3, right? Okay. And then I subtract 2. And then I do the log base 4, right? I multiply by 3, then I subtract the 2, and then I've got this log base 4, okay? And then I add 12. Okay, so let's unwrap. Again, I'm working upwards now, right? I'm working this way. So I'm going to unwrap the plus 12 first. I'm going to subtract 12. Okay, that's not so bad. Subtract 12. I get 3 on the right side. Okay, now the next thing I want to do is I want to unwrap this log base 4. Okay, how do we unwrap logs? Well, the inverse is exponentiation. What that means is I'm going to change the form. I'm going to do 4 to the 3 equals 3x minus 2. So this is the step of line number 3 says to change the form. Change to exponential form. That's really our new step here. That's really the new thing to get out of this particular problem here. Because after this, notice what happened here. This now is just a really simple algebra 1 problem, right? I can add the 2 and divide by 3, and I'm home free, and that's it. And divide by 3, and I get x is going to be 22. And again, I'm going to go ahead and check that, but I just want to reiterate what we did here. I'm going to go back to the chop for a second. Okay, so again, there's one variable, there's only x one time, and I want to unwrap here. So again, I made a list over here of what happened, how did I wrap up x? Well, I multiplied by 3, minus 2, log base 4 both sides, and then I added 12. So I'm going to unwrap those. And the key step for us here is when we took the log base 4, to unwrap that, I changed the exponential form. Again, logs and exponentials unwrap each other, they're inverses. So that's our new thing here, is to change to exponential form. Just like before the exponentials, we took the log of both sides. Okay, so I'm going to go ahead and check this and make sure that this works out. So I'll do a little side note over here. Log base 4 of 3 times 22 minus 2 plus 12. Ooh, really running out of room. Does that equal 15? Well, question mark on that. Okay, so log base 4. Let's see, this is going to be 66 minus 2 is 64. Plus 12 equals 15. Okay, so now I'm looking at this and I'm saying, okay, 4 to what power equals 64? Well, that's 3. And 3 plus 12 is 15. I don't need to write the last line. I know that works. I know 3 plus 12 is 15. So again, I'm checking these just to make sure that my answer that I get actually works in the original problem. So we're going to get some extraneous solutions somewhere along the way here. Okay, let's look at one more. I'll give you guys a couple practice problems, and then that'll be our day. Okay, so last new one here. Okay, so notice how, okay, there's a logarithm on both sides. There's 2 x's here, right? There's an x on both sides. But something really nice is happening here. This is really nice. Okay, notice how on both sides it's log base 7 on both sides. Those are exactly the same. So this is kind of like that exponential problem at the very, very beginning where we ended up with the same base eventually. This is already starting with the same base. So these arguments, the x plus 3 and the 8x plus 17, they must be the same. Right? If these 2 sides are going to be the same thing, and those bases are the same, the arguments must be the same. So really, in one move, I've really simplified this problem. and now you're down to an Algebra 1 problem. Okay, so I'm just going to clean this up rather quickly here. Subtract x. I'm going to subtract 17 at the same time. And I'm going to get 7x on the right side. I'm going to get minus 14. And I'm going to get x equals negative 2. And I'm certainly going to check and make sure that I get a negative value here. And that's a big red light for me with logs, right? Because taking the log of a negative is a problem. So I'm going to check this out. Log base 7 of negative 2 plus 3, does that equal the log base 7 of negative 16 plus 17? Okay. Well, log of negative 2 plus 3 is going to be 1. So is the log base 7 of 1 equal to the log base 7 of, oh, I get 1 on the right side as well. Well, those are both the same thing, right? In fact, they're both 0, right? Log of 1, any base is 0. Okay. So, again, it does check out. That's really nice. But this is kind of one of those, it's really kind of a special problem. I'm not sure we're going to see these too much, but there's certainly a useful thing where we have the same basis here, right? So those arguments really need to be the same. Okay, so take a shot at these two problems here. I'm going to enlarge these for a second. Go ahead and pause it now and take a shot, and I'm going to put the answers up right away here. Okay, so the key to this first one, and I'll just start you off on this, these both need to be written with base of, you can use 9 or base 3. 81 certainly can be written as base 9. And when you do that, I'm going to let you guys clean it up from there. You should get x equals half. And over on the right side here, I'm going to just let you guys clean this one up here. The solution, you should get x is 61. And again, that's just a nice little unwrapping. Add the 5, change to exponential form, and you should get x equals 61 here. So hopefully this was a good little practice, and hopefully this let us accomplish our goals of solving at least 2 exponential equations. We solved at least 2 logarithmic equations, and hopefully those last 2 that you're actually able to do on your own. If not, get ready to ask some questions in class tomorrow, and we'll pick it up right there. Thanks a lot, and have a great day.